box, so that's not
Right.
right. So factor group. Factor groups. Right, so that's what we were doing. Remember, we said the normal subgroup is a subgroup for which both the left cosets and the right cosets are the same, and then we had the equivalent condition, so it's close under conjugation, whatever conjugation is, we'll come to that later. Now, what we said is that if you have a normal subgroup, you can create a new group, which is called a factor group. Oh, I didn't say it was a factor group. So this group is called the factor group. G over n. Well, the elements in this group are the cosets of the subgroup. And there's an operation where you can take, that's what we discussed yesterday, you can take any element from each of the two cosets, and when you multiply the two elements in the group, you get the element that defines the coset as a result. Okay. And we had proof that it's actually a group. So firstly, what we looked at was whether it's an operation, so whether it's actually well defined. So whether no matter which two cosets which two elements you take from the two cosets, but you always get the same result. We proved that you always do get the same result. So now what we're left with is showing that it actually is a group. Right, and what do we need? What conditions do we need for a group to be a group? Well, I guess we need to show that it's closed under this operation. Okay, so if you take a coset and another coset, which is, I mean, this is trivial, right? So you get ABN is also a coset. So yeah, so that's good. Should be associative. So if you take this coset and this coset, get the result, times it by this coset. Well, what do you get? Well, this you get the coset of AB. This you're timesing with the CN coset. Okay, so what do you get? Well, ABC, the coset of this element. Now, because the group operation is associative, you get ABC, right? The coset of this element, and of course this is this coset times by this coset, and this is this coset times by this, and there's really nothing hidden in there, because normally one doesn't even write the brackets just because they're all the same thing. You don't need to write the brackets at all, but I've done it in all detail so you can see that it's justified. Now next, oops, sorry, I didn't want to take it just in case somebody's copying. So next you want to show that there is an identity element. Okay, so is there an identity element? What would an identity element be? E is it's in the group, but we need a coset. So remember the elements of the factor group are the cosets. So we need a coset which will be the identity in this factor group. But a natural choice, of course, is the coset of the identity, which is subgroup itself. Well, why is the identity? Why? Because if you take En times it by An, well, by definition, you get the coset of Ea, which of course is An, which of course is the same going backwards. So it's also An. So that's the identity. And an inverse is, well, again, there's nothing unexpected there. So if you have this, its inverse is you invert the element and take its coset, and then you times this by that, you get, well, you get, okay, and that's the same thing again going backwards, so this is the same as AM. Oops, keep running out of space, sorry. Sure about that. Okay, so this shows that it indeed is a group. And the last thing that the theorem claimed was that its order is, so the order of the factor group is this. Well, that is really so by definition. Because, well, the elements of this factor group are the cosets, and this thing, the index of n in G, is defined as the number of cosets. So, really just that. Okay, that's the end of the proof. Now we have how we can do factor groups. Well, for two reasons. Firstly, because this works. And secondly, because n is a subgroup, so it's close on the inverses. So if you take all the inverses of everything in n, you get n. Pardon?
Doesn't make sense.
What exactly?
All that inverse part. Would you want to replace again?
I could do. Yeah. So you have the set of all cosets. Trying to say that it's a group. If it is to be a group, you need every coset to have an inverse. So if I get an arbitrary coset of this element A, you want to know what its inverse is. Well, I'm telling you, you take the inverse of A, and the coset of the inverse is the inverse of this coset. And to prove this, you just calculate that it actually works. So, okay, let's do some examples, maybe it will become clearer. So what's called example 10.5 in the book is example 10.2 continued. And in example 10.2, we had n was consisted of permutations, the identity permutation, this 3 cycle, and then we said that it was a normal subgroup of the symmetric group of all permutations on 3 letters or 3 elements. Right. Now, if you want to know what S3 by n is, one way of doing it is you look at the Cayley table. The book does. Does it not, Danny?
It does.
So n is the identity, and then there's the second element, which is a coset of a transposition. Well, actually, all the transpositions are in it. I think. Well, definitely, because they're not there. So n times n, well, it has to be n, and this is just this, and this is just this, and this is just this. Okay, so it's not much of an example. So which group does that remind you of? It does indeed. Helps to have the book open. Okay, but then again, there's only one group and two elements, so what did you expect? Okay. So now you can see, like, the elements, but the elements of this group are not the numbers 0 and 1. The elements of this group are this set and the remaining 3 permutations. Yeah, so there are 6 permutations of 3 elements, the identity, this cycle, and that cycle, and then there are the 3 transpositions. That's the other set. Okay, I'll make the it. So 1, 2, n is, that contains the transpositions 1, 2, 1, 3, 2, 3. And that's all the permutations of the 6 elements. So the elements of factor group are not the numbers 0 and 1. They're this set and that set. The elements of Z2 are the numbers 0 and 1. So that's why they're not equal, but they're isomorphic, which is a concept I you should know. Sweet. Okay. But isomorphic is well, whatever. I'll shut up now. So somehow, okay, so this somehow this n, that's all the even permutation. And 1 to n is all the odd permutations. So what this does is the isomorphism captures parity. Yeah? When you multiply two odd permutations, you get an even one. When you multiply odd with even, you get odd. So this is what this isomorphism of the factor groups does. And there's homomorphism. Well, you've not done homomorphisms yet. But that's okay. I mean, more generally, one could do. One thing we observed is that a subgroup of index 2 is always normal. Yeah. I'm trying to tell you that there is a group which is called a factor group. So more generally, one can take the alternating group, so that's all the even permutations, and that's again, it's always going to be just a 2-element group. Isomorphic to it. Stick them off. Make the effort. Smile. She always does the smile.
Oh, I did miss the smile.
Okay. Okay, so what is this kind of good for is, yeah, you're building groups from smaller pieces. Kind of like In some sense, Sn is not, well, we'll see that it's called simple, but you can see some structure within Sn, yeah, because there is like this odd and even. Okay, so what happens in Sn from not from a permutations group perspective, but from looking at the structure of what Sn is like, is you can see that Sn kind of split into two bits. Okay? It's the AN and it's the other one. So let's say 1, 2 AN. And you know that what happens within the normal subgroup, you somehow know what that is, or maybe you want to know more, but okay, you know what that, you know how this works. And now you know that between the two groups, it works like Z2 between the two concepts. So you want to see what a group behaves like really internally, and this is a way of looking at it. And in fact, if you could go on. So you could look at AN. Can we split it into some other group of cosets? We cannot, as we will see next week. So kind of AN is like a basic building block. Sn is not a basic building block because Sn you can build from AN and Z2. Okay. So that's what this is trying to do. And so for now, just accept it, but then Killian will be doing chapter 13, I think, at some point, maybe in the new year, which is about the structure of groups. And this is where it comes up again. So it's kind of trying to analyze what the internal structure of a group is based on trying to break it into smaller parts. So that's what it's going to be good for. This is example 10.5. Now, example 10.6 is again, you've got, this is you take all the multiples of Z, and that's a normal subgroup in all the integers with addition. Wow, why is it normal? And one thing we said is that any subgroup of an abelian group is normal. So the cosets, what are the cosets? Well, of course, you have NZ, which is the subgroup itself, which is the coset of 0. And you have 1 plus NZ, 2 plus NZ, and minus 1 plus NZ. Okay. They're the parity, no, what they're called, modular remainder classes, modular n. So what's the factor group? Got it yet? What's the factor group? Well, what are the elements? The elements are these cosets. Okay. And how do they operate? Well, you know, for example, if you take these two cosets, what do you get? You get the coset of 3. So this is isomorphic to MZ. Not MZ, but then with addition modulo n. Okay, so example 10.7. What's the dihedral group? Symmetries of the end-on, regular end-on. By now you well know that it's generated by a rotation and a reflection. No, that's not how you write reflection. Whatever. What is it?
No, we'll try it. It's
Oh,
not
no, there's no X. I'd write it with an X. It looks better. Okay, so if you take all the rotations, so you take all the, okay, there is this R to the n is the identity, and S squared is the identity, and then there's SRS is R inverse. Yeah, so if you reflect, rotate, reflect back, it's like rotating the other way. There's a kind of the presentation equalities or whatnot. And now, if I take Rn, the subgroup generated by R. So this consists of all the rotations. So here, are you okay? Yes. Well, it really is. If you do the reflection, then rotate it, and then the reflection is like rotating it backwards. Okay. So this consists of all the rotations. It's a subgroup. Of course, it's a subgroup because it's a subgroup generated by R. So how could it not be a subgroup? But the question is it a normal subgroup? How do you know? That's a B. Well, rotations are, yeah, well, I guess, I mean, one way of showing that it's normal is you say the index is fluid. Because all the elements because what? So the order of Rn is n, the identity, and then all the other rotation, n minus 1 rotations. The order of is 2n. So the index 2. Okay, so we said again, we said this is starting to be silly because what we're getting here is again we have Z2 as a result. So in this sense, the book is slightly disappointing because all the examples just lead to Z2 or Zn. You know. I mean, so what is, so in which sense is this now? And so when we were talking about the even and odd permutations, what it did was it captured the parity of the permutations. But here it captures something else. Well, namely, what it captures is whether the symmetry is what, kind of like a mirror symmetry or a non-mirror symmetry. And so all the rotations where the numbering still goes clockwise in the rotations subgroup, and all the symmetries where numbering starts going counterclockwise, they're in the other cosets. And if you do two of the latter, then you get one of the structure. Does it make any sense? Basically, what it's saying is that there is some kind of overarching structure of the group, in which you have a subgroup that does something, which is of dependent interest, but and then there's another coset of that group, which kind of does the same thing, but how it works among the cosets is captured by a different structure. So not to be disappointed, I've added an extra example. Oh, it's in. Or just because you said. So what is GL 3R? Yes. So it's a general linear group, which is all the 3x3 invertible matrices. Okay, so non-zero determinant in particular. And then there is SO3. That's the special linear group. So these are the 3x3 invertible matrices over R with determinant equal to 1. Okay. So that's a subgroup. Is it normal? It's not index 2, it's not even finite index.
This is an example. Yeah, I feel like so
Yes. Yes. Okay. Okay, so how does one, okay, so why? So how would you, so, right, so why is it normal? Okay, it's normal because, so one of the conditions of being normal was that if you take G and G inverse, this was supposed to be a subset of N. So N is normal if, only if, for any G in the big group, when you do G and G inverse, you get something inversible. Condition 2 in theorem. So what does this translate to? That translates to general matrix A, a special matrix S, and this. So let A be a general linear matrix, and S be a special linear matrix. They're not called special linear matrix. So what is this? We want to show that this belongs to the special linear group. So what we want is that this is in the special linear group. Now that one, remember, is defined by having determinant 1. So what we want is the determinant of our set inverse, which, as you know from Stephen, the determinant of the inverse matrix is 1 over the determinant. It's multiplicative function. So this is so yeah, it's a normal subgroup. Okay, what are the cosets? What are the cosets of this? We did this example in one of the tutorials, I believe. You know? I don't know. The question is. Oh, but that's completely different. I'll figure it out. For homework, you can do it with 4x4. Now, right, so each of the cosets was defined by having the same. So the cosets having the same determinant. So the cosets. Well, the cosets are fixed, the real number t, non-zero. You look at all the matrices that have this fixed value of the determinant, and that's a coset. Okay. Now, what happens when you times two cosets? You get another coset. And the determinant is going to be the product of the determinant. Because if you, so if you take A, that's one coset, you times it by B, you get the coset of AB. So these have the determinant, so these are all this coset, that's all the matrices that have the same determinant as A. This coset is all the matrices that have the same determinant as B. This is all the matrices that have the same determinant as AB, which is the same as the product of the two determinants. So really what it does, the only thing it does is multiplies real numbers, doesn't it? So now you're starting to see the light of the image. I can't remember what the, I think it's called star in the, so the multiplicative group. non-zero real numbers. No, I don't know what to do. So there's something I wanted to do that also is not in the book. I'm not sure we have enough time. Okay, so just as a side remark, it's not going to be on the event. Or maybe it will be. The remark, the essence of the remark is that we need normal subgroups. And the actual meaning of this is the following. So suppose you have a group. You partition it in any way. Into subsets. Okay, so partition group G into subsets. Now, hopefully you know that a partition goes hand in hand with an equivalence relation. Okay, so define a relation. What does Killian say? John. On G, by saying that A tilde B if A, B are in the same subset of the partition. So one way we were partitioning the group into subsets was into cosets of a group, of a subgroup. But now we're not even assuming that there is a subgroup or anything. We're just assuming that partition. Okay. Now what we wanted, Kim's theorem, was that we had this property that we wanted a subgroup. Sorry, we wanted a factor group on the subsets. So we wanted to take two elements from two different, or even the same subsets, and when we times them, we looked where the product was. We wanted to get the same subset every time, no matter what two elements we chose. Okay, so that was what we were proving. So when we had A from here and B from there, and then we took another different A and then different B from the same subset, we always wanted to end up in the same subset, because otherwise it wouldn't even define a factor group. It wouldn't be an operation. Right? That was kind of the basic idea.
Yeah, yesterday.
You were supposed to draw it yourself. Now, okay. Now, if you okay, so one way of getting such a thing was we got a normal subgroup and its coset. So we know that. Now, question is, can we do something else? Okay, so we want want this to satisfy that if A and A dash are in the same subset, and B and B dash are in the same subset, then products are also in the same subset. Maybe it's 3 different subsets, but anyway, now, so such an equivalence relation is called a congruence relation. Okay. Now there are a couple of things that one can observe. So, prove. So if you have 2 elements from the same subset, then their inverses are also in the same subset. That's the first thing that one can prove. Well, that's like an exercise. And but that's not so important. What is more important is that if you look at the equivalence class of the identity, so that's all the A's in G, G's in G, which are in the same subset. This is a subgroup. Okay, why is that? Well, so I'll call this M. If G is in N, then G is equivalent to E, congruent to E, to the identity, by definition of N. And by, okay, I'll call this 1. It's 2. And by the first bit, we have G inverse is congruent to E inverse. Well, that's just the identity again. So inverses of elements are set. And if you have 2 different G and H in this set, then they're both congruent to the identity by definition. Then there is a congruence relation, right? So So if you do GH, so it's a subgroup. So what we want to show, I think we'll come back to it next week because we're out of time. It's really nice. Is that then you want to show that n is actually a normal subgroup, and the subsets in the partition are actually the cosets of n. So if you start with a situation that looks like this, then the only way you can have something like that is coming from a normal subgroup. That's the idea here. Okay. Any questions? Come on then.